Hello, everybody. My name is Zachary Minken, and I'm going to be talking to you today about a research study that I was a part of with my dissertation chair, Augusto Macalalag, and a colleague of mine, Naja Naylor. Together, we were part of this research study that led to a paper that we published titled, "What Will You Do to Help Elementary Students Who Struggle in the Engineering Design Process? Analysis of Teachers' Reflections, Fundamental." So as you can tell, maybe right away, we're going to talk about the engineering design process and what that is and why it's important, and what that has to do with education and what teachers sort of think about it and throughout this whole process. The fundamental that you see over here, this was because the conference proceedings that this is published in, they require a little bit of a tagline so that they know what category you're a part of. So that's our category. We are fundamental. Again, I'm Zachary Minken. I did this work with my dissertation chair, Augusto Macalalag, and my colleague, Naja Naylor. So let's dive right in. So engineering design process, this is really the main concept that our whole study revolves around. And if you're not familiar with it, it's essentially, if you're familiar with the scientific method that maybe you learned in science class, the way that scientists solve problems and learn new things, this is sort of like that, but for engineers. So the engineering design process, or EDP, I may say EDP sometimes, so now you know what that means. The EDP is essentially the scientific method for engineers. So it's a way that engineers can solve problems, like real world problems. So we'll talk about that in just a second. If you look over here, this is a diagram of the engineering design process. So it sort of, as you can see, it centers around the goal. So maybe maybe we're thinking about designing a car that is more fuel efficient. So you know that is our goal. So then we start, and I want to preface this. There are a lot of different versions of the engineering design process, but this is a common one, and this is the particular one that we use as sort of an analysis tool in our study. So it begins with this step right here called ask. So in this stage of the engineering design process, what you're doing is really defining the problem. So our goal, right, is to build maybe a car that's more fuel efficient. And in this stage, this is where we're going to say, so how much money can we spend on this? What are some of our constraints? Like, how much money can we spend? What materials are we allowed to use? How fast does it, need to go? How many people need to ride in it? What kind of roads is this thing traveling on? Are we building an off-road car, one that's going to travel on paved roads? What types of fuel are we allowed to use? Does it have to be gasoline? Can it be diesel? Can it be maybe a greener fuel like solar power, or an electric car? So this is where we sort of define the problem for ourselves. Then we kind of move clockwise around the circle. So then we get to imagine. Imagine is like your brainstorm. So once we have a handle on our problem, this is where we sort of brainstorm different ideas. Like maybe we have an idea for a four-wheeled car that seats two people, that can travel 60 miles an hour on solar power. Maybe we come up with another idea for a three-wheeled car that is going to use regular gasoline and can seat four people. But maybe it'll have a special type of engine that's maybe more fuel efficient. So you would come up with some different solutions here, and then we go into the planning stage. So plan, this is where we pick one. Maybe we want to go with the solar powered two-seater, and we think about all the different materials that that we're going to need uh, to make this happen. Then we move from plan to create. So in this stage, um, in this stage, we are building our car. So we're thinking, we're working together with our team to get the materials, assemble it, and we have our car. Once we have our car, we move into the improve phase. So the improve phase is where you kind of take what you have and you test it out. You see how well does it work? Can we make it work better? Things of that nature. And you'll notice this is still a circle, and we can continue right back to the ask if we want to further define our problem, like in what ways can this be better? What extra materials do we have left over? How much of our budget did we not yet spend? How many people do we have to help us out? Is there research? Are there people who already did this that we can look at? So this is really meant to be an iterative process. So the thing is, and you see this over here, maybe you think I skipped it, engineering design process is not something that's frequently taught in schools. In fact, if you're not, someone who's very interested in science or engineering, you may not have ever heard of it before. If you have, you can thank your teachers. But it's not frequently taught in schools, and this is for a whole host of different reasons. One of which being that a lot of teachers just struggle with the concept and don't really know well how to teach it. Despite the fact that it has there's a research base that does show that there are plenty of benefits for teaching the engineering design process in schools. Things like improved problem solving skills. You might guess that because this is really a method for solving problems, but also increase engagement and motivation in STEM subjects, that's science, technology, engineering, and math. So because of all this, we based our study around this course, this Introduction to STEM Education. So this is a course that was developed and taught by my dissertation chair. It has some objectives that you can read over here and some core assignments that you can see in this area. But the main thing is that this course was designed to kind of correlate with the framework for science teaching, K-12 science teaching, based on these next generation science standards. Really, the idea is moving towards an integrated approach to teaching science, technology, engineering, and math, and to sort of shift from learning about it to learning to do it. So you'll notice some of the core assignments down here at the bottom. We're writing a teaching statement, developing and implementing a STEM unit, watching video captured lessons, but also the pre and post tests. So the pre and post tests were the thing that we focused on most for this study, and I'll talk about that more in a little bit. But just to give you an idea about the sort of the nature of the course. So it was really geared to be like a hands-on approach to learning about STEM education with a focus on the engineering design process. For instance, the students in this course who were really teachers, but so one activity that they did was they worked in groups to design a rubber band powered car. So working in groups with a particular set of materials, they had to design the rubber band car that could go the farthest distance. So it was a little bit of collaboration as well as competition. And this is something that you can easily think, well, yeah, there we go. We can apply the engineering design process right away. And that's one of the things that the research shows, is that teachers need more professional development and, really just in and around what the engineering design process is and how to use it, and specifically how to use it with students. And that was, again, that was really the goal of this course here. So with that in mind, with this study, and with the paper that we wrote, we had two main research questions. You can read them here, but we were mainly interested in, obviously, how does the course affect, teachers, particularly in terms of the engineering design process, the EDP. So we were interested in this in two ways. The first being because how do teachers' knowledge of the EDP change? Because the research shows that teachers don't use the EDP as an instructional tool in classes because they're not very familiar with it. They don't know a lot about it. So, to what extent are we improving their knowledge with this? The second question was more about this pedagogical moves to scaffold students' learning experiences of the EDP. So what we mean by that is just teaching strategies, right? So, teachers need to know what this is, but then they also need to know how to teach it. So we were looking at sort of from these two different perspectives, related but distinct perspectives, to see what happened with our teachers throughout this course. So a little bit more background. So we had, and I mentioned this earlier, there were 17 teachers in the course. So we, in the course, maybe, they were students, but really they were practicing teachers, in-service teachers, particularly elementary teachers. Most of them had 7 or more years of teaching experience. The other ones obviously had less than that. Also, the majority did have a background in early childhood or elementary education. Additionally, these were suburban teachers, so they all taught in the same suburban school district. So our main data source, as I alluded to earlier, was that pre and post test. So at the beginning of the course, the teachers were given a test, multiple closed and open-ended questions, and at the end of the course, they were given that same test. For the purposes of this study, we were looking at just those four of the open-ended questions on this test. Particularly, these were questions that were related to, they were designed to measure teachers' knowledge and pedagogical skills regarding the engineering design process. They were all based upon a scenario where, you imagine you're part of a team of scientists and engineers, and you are, as part of a scientific investigation that you're doing, you are scaling Mount Everest. And as you may know, Mount Everest is cold. So, what you may not know is that the temperature degrees vary widely as you go from the base of the mountain all the way up to the peak. So, with that in mind, the scenario is that you need to design a coat that will, be suitable for this trek. And it's all very cold, but as you go up, it gets much, much colder, right? So you don't want your teammates to be overheating at the base of the hill, at the base of the mount. This is Mount Everest. But you also, don't want them to be freezing when they get to the top. So that was the crux of the question. There were sort of 4 different elements on that. The first was just, so what would you do, right? What steps would you take to solve this problem? The next question talks about it in terms of, you just did this, you just gave this scenario as an engineering design challenge to your students, right, to your class. And you have some students who start, making this coat right away as soon as they get the materials. And, the teachers are asked, what steps did students skip? And also, what advice would you give them? Then The last question that we analyzed for this study was, again, the same scenario, but this time, and also still having given this scenario as an engineering design challenge for your class. But this time, thinking about you have a group of students that is disagreeing over the color that they want to make the code. And the question is, so what would you do in this situation, right? How would you handle this as a teacher? So all these questions are sort of designed, again, to help us measure teachers' knowledge of the engineering design process, but also their instructional strategies when it comes to teaching the engineering design process. So the way that we analyzed this data was, so this was qualitative data because it was, this was qualitative data because, these were open-ended. So we had a lot of words to look through. So what we did was I developed a coding manual that consisted of two different types of codes. These EDP content codes, which were aligned with teacher knowledge of the EDP, but also teaching codes designed with the instructional strategies and practices for EDP. This way we could look at both of our research questions. So the content codes, and all of these, let me preface this, all of these codes were developed, I developed them basically by sort of immersing myself in the data, reading and rereading all of the different responses from the teachers, and and just kind of coming up with some salient themes, maybe words that kept repeating or ideas that kept coming up. And I kind of narrowed those down until I had my codes. When doing the whole coding process, before I had even gotten these, we made sure that the tests were de-identified and just given numerical codes, so that later we were able to match them up and see which was the same person before and after. But during the process, we didn't know which tests were pre-tests and which tests were post-tests, or who had which test. So some of the content codes that emerged were the ideas of research, interviews, brainstorming, planning, prototyping, and mathematics. The teaching codes that emerged were the idea of slowing down, use of analogies, argument from evidence, data analysis, discussion, redirection by teacher, and researching other groups. For those of you who maybe aren't as familiar with the term redirection as it applies to education in the classroom, redirection is when you have students who are doing one thing, but you want them to be doing another. So, maybe they're just not doing the work you asked them to do, or maybe they're misbehaving. And so you are redirecting their focus and their behaviors from one thing to another. So that's what we mean by redirection. Now, 100% of these tests were double-coded. So what that means is that after I developed this coding manual, I trained another person, our third author, Naja, on how to use this coding manual to identify whether or not these codes were present in a given test, for a given question in a given test. So we each coded all of the tests. So I coded 100% of the tests, she coded 100% of the tests, and then we compared our notes and said, well, this is what I saw, what did you see? This is a way of sort of ensuring some measure of reliability, that we really are seeing what we think we're seeing, because you can imagine that this might otherwise be a very subjective process. So having that extra person to independently look at the same set of information is really helpful in establishing some credibility and some trustworthiness in your results. So we had a 90% agreement or better for each question. So when we disagreed, which happened occasionally, not that often as you can see, we discussed them, we negotiated, we decided if we could come to an agreement, maybe, I just wasn't looking at something, or, maybe we actually fundamentally disagreed. So we then decided, what we didn't agree upon, and the things that we agreed upon were included in the report. And then essentially, because we had qualitative data, but we did a quantitative analysis of that data. So we looked at we essentially, if the code was present in a particular test, in a particular question in a particular test, then we would put a 1. And if it wasn't, then we put a 0. And so what we did was we, kind of added all of that up and compared the results from the pre-tests to the post-tests, so that we could look at quantitatively a change over time in the teacher's knowledge and teaching strategies with respect to the engineering design process. Now, our first finding was relating to teachers' knowledge of the engineering design process steps. So what we found was that from beginning to end, after, so we think as a result of taking the course, the teachers were able to understand more deeply the engineering design process, particularly the steps of brainstorming, planning, and prototyping. So these were 3 of the codes that had emerged. So you may remember the original version of the engineering design process that I showed you. So brainstorm, this is our imagine code. Plan is still plan. And prototype is sort of a combination of creating and improving. So you can see these graphs right here. So the first one is talking about that first question. When we gave you the scenario and we said, so what steps would you take to solve the problem? So you can see this is just a percent difference from beginning to end. So below this line right here, this means that there was a decrease. So less people said research at the end than at the beginning. And here you see there's, here's brainstorm, plan, prototype. And you can see they are, all well above a 20% increase from beginning to end. When thinking about just teachers in general, this is their knowledge, right? What would you do? What steps would you take? So at the end of the course, they were talking much more than they had been previously as a whole about brainstorming, planning, and prototyping. Over here, we have, what did students skip? So this was the second question where we said, so you give this to your students and one group starts working right away on building their materials. So building their code with the materials. So, think the create step. And so in here, again, we have the teachers talking more about brainstorm, planning, and a little bit about the prototyping as well. So this is good because in the research, it's good because look, we did something. Now it looks like the course was somewhat effective, but also particularly because the research that's currently available shows that oftentimes what teachers struggle with most is the stuff at the end of the process, the prototyping, the creating and improving. So the fact that this is increasing is very, very encouraging. Our second finding, we'll move on to the second finding, was about instructional strategies. So this is thinking about, so at the end of the course, this we noticed that the teachers seem to have a greater understanding of the importance of planning and prototyping to EDP. So what we mean by this is this comes from the third question. So again, that scenario, you give this challenge to your students, and one group starts working right away. Um, what advice are you going to give them? So, now we're thinking, so we see this and, we know they skipped some steps. What are you going to do now? What are your teaching strategies? So, um, again, um, you see, so this is the blue represents what teachers were saying before at the beginning of the course. The red represents what they were saying at the end. And then you see over here, this is the same type of percent difference graph. So what you see just, by looking here, so the first thing, this is why I include both, because if you look at just the percent difference this time, you see this huge decrease in research and a very big increase in prototype, and a very small increase in plan, right? But when you look at the bigger picture, you see, well, we had a lot of research at the beginning, and we kind of shifted from saying you need to do some research, you need to define your problem, to you need to really plan and you need to prototype. So the plan, even though plan was only a slight increase, you see it's already one of the highest codes here. Additionally, when you see prototype, you see at the beginning, nobody said anything about prototyping. No one said, you need to work on improving, you need to, think more deeply about, your process and testing things out and making sure you know what you're doing. But afterwards, when thinking about giving advice to students, now teachers are really recognizing this importance in prototyping, which is also really, really good to see. Then our third uh, finding here, this one was the most surprising. Actually, you might notice we had 2 research questions, but we have 3 findings. So the third one was kind of a surprise. So this came from our last question that we asked them, which again is thinking about the instructional strategies. It was, so now again, you've given this challenge to your students where they need to build this coat to scale Mount Everest, but you have a group that's disagreeing and they can't agree over things like the color of the coat, and you're the teacher in the situation. What do you do? So what we found was that at the end of the course, there was a much bigger emphasis from teachers on data analysis. So looking here again, this is the blue is at the beginning and the red is at the end of the course. So what you see is a couple, you see 3 main increases, right? You see with researchers a little bit of an increase. You see an increase with prototyping, saying the need for testing things out. But coupled with that was this humongous increase in the idea of data analysis. In other words, teachers saying that to students, well, listen, where maybe before they were doing more redirecting and saying, well, there were teachers who said, well, this isn't a big deal. Just pick something out of a hat, right? The problem is that we're disagreeing. So let's just pick something and move on. This isn't important, right? But then at the end, you have teachers saying, well, you know what? Is this important? We don't really know, right? Maybe the color will be effective or have some kind of difference. So let's design a test to test things out. Let's look at, what happens when we have different colors. And we had a lot more teachers at the end talking this way. So this, this is really showing that, the teaching the engineering design process, you would think if teachers are, if they're teaching with the engineering design process and one of their big instructional moves is saying, is sort of encouraging students to do some data analysis, to, to test things out, as a means for resolving disagreements. Because that's the other piece. This question was particularly, yes, it was about instructional strategies, but particularly when you have student disagreements. So the idea that teachers are, through the engineering design process, thinking more about teaching students to resolve disagreements through actually data and inquiry, is really, really cool. At least I think so. Um, those were our three findings. So just to kind of wrap that all up, we were looking to see, again, how teachers' knowledge and pedagogical moves changed over the course of this class that they took. Upon analyzing all of our data, we found that at the end of the course, our teachers had a much deeper understanding of brainstorming, planning, and prototyping, being important steps of EDP. Secondly, we found that more teachers at the end of the course were recognizing the need for explicitly teaching planning and prototyping skills to students. So this was, again, the instructional strategies, these pedagogical moves with EDP. And then the third finding, which I just got done talking about, is that teachers' focus had shifted to data analysis as a means for solving disagreements, right? So this is really cool because it does suggest a sophistication. Really thinking about prototyping as being a major piece of the engineering design process, and this data analysis being an important part of that. Because again, the literature does show that one of the struggles that teachers tend to have, even after professional development courses, is that they still struggle with some of the later steps, like this prototyping, or the improving, as it was called. So that's what we found. Now, obviously, like with any study, we had some limitations. The main limitations are really coming from the fact that we didn't actually see what happens when these teachers get into actual classrooms. We didn't videotape them teaching lessons. We didn't go and observe them teaching lessons. We didn't look at student work samples. We didn't have teachers reflect on actually having taught the lessons. It was really just, increasing teachers' knowledge with, the understanding that teachers' knowledge of content and how to teach it is very much related to what happens in their classrooms. Additionally, through the course, the teachers were also engaged in domain-specific knowledge. So in other words, specific scientific concepts. So when we think about the coat again, and the students having disagreement over the color, if you remember anything from physics class, you may know that different colors actually do different jobs at absorbing or reflecting light and heat. So, but we didn't really measure the effect of that domain-specific knowledge on the EDP. In this particular study, we didn't really look at it. So that may have had an effect, but from the study, we can't say. And then, again, like I said, because we didn't actually observe the teachers in the classroom, we don't know how well they implemented what they learned. So that is going to be something for future research. So that is my presentation. Thank you so much for listening, and I believe we're going to be doing a live question and answer session at some point, so they will send you the information, and I look forward to speaking and discussing this with some of you then. Thank you so much.